Today I'll be talking about chapter 5, the 3 states of matter. I will cover in this video part 1, gases and the kinetic theory of gases. I'll provide a link in the description of the video for the material. We all know that there are 3 states of matter: solid, liquid and gases. Solids have fixed volume and fixed shape, while liquid substance flows freely but of a constant volume. It have a consistency like that of oil or water. For gas, it is the substances that have very small intermolecular force and have no fixed volume. So let's first talk about gases. First, we need to know what is the kinetic theory of gases. To start with the kinetic theory of gases, we need to know the term ideal gas. In studying any gas, I have to consider 3 parameters: pressure, volume and temperature. For ideal gas, the ideal gas have a volume that varies exactly proportion to its temperature and exactly inverse proportion to its pressure. The kinetic theory of gases explains the continuous motion of gas particles. In case of ideal gas, kinetic theory states that the gas molecules move rapidly and randomly. Also, the distance between gas molecules is much greater than the diameter of the molecules, so the volume of the molecules is negligible. There are no forces of attraction or repulsion between the molecules, and all collisions between particles are elastic. This means no kinetic energy is lost during the collision. The temperature of the gas is related to the average kinetic energy of the molecules. So, if gas doesn't behave like ideal gas, what we should name it? Actually, we should name it a real gas. So, a real gas is a gas that doesn't behave like ideal gas. In noble gases such as helium or neon, the intermolecular force are so small, so the gas approaches the ideal gas behavior. But for the rest of gases, actually, it behaves differently. This is why we name it a real gas. The volume that gas occupies depends on 2 parameters. First is the pressure, and we measure the pressure usually in Pascal, and the second parameter is the temperature, and we measure temperature in Kelvin. So if I have any Celsius temperature, we should add 273 to be able to convert it into Kelvin. As for if I have kilopascal, I should multiply by 1000. So let's find out the relation between the volume and pressure. This is what we call it gas law. Gas law states that at constant temperature, the volume of the gas is inversely proportional to its pressure. If we looked here at this figure, we could see that the volume here is smaller than in that case. So, and the particles of the gas are moving here and collides more often than in that case. This what makes the pressure of this figure is higher than of that state. If we try to draw the relation between the pressure and the volume, we will see that it forms a curve. So what about the relation between the gas volume and temperature? This is what we call Charles' law. Charles' law states that at constant pressure, the volume of the gas is proportional to its temperature. This means V will be proportional to T. So if I heated gas, this means the volume of the gas will increase by increasing the temperature of the gas. If I try to draw the relation between the temperature and volume, it will give me a straight line. As if I looked at the relation between the temperature and the pressure, this is Lussac law, and this law states that at constant volume, the temperature of the gas will be proportional to its pressure. So if I looked here at this gas, if I increase the temperature of this gas, the particles of the gas or the molecules will start to collide more often, and my pressure will increase. So if I try to draw the relation between the pressure and the temperature, it will give me a straight line. So the ideal gas will have volume that is proportional to the temperature and inversely proportional to the pressure. So there are few limitations of the ideal gas law. First, it assumes that there is no attraction between any molecules. Also, during calculation, we should ignore the volume of the molecules. While if we looked at high pressure and very low temperature, we will find out the molecules are so close together. This means the volume of molecules is not negligible compared to the volume of the container. Also, there is a considerable attraction forces between molecules. This would be either van der Waals forces or dipole forces. The attraction forces will pull molecules together and away from the wall of the container. The pressure would be lower than the state of the ideal gas, and the effective volume will be smaller than in case of ideal gas. So if I'm asked what is meant by the term of ideal gas, this means I have a volume that varies exactly in proportional to the temperature and inversely proportional to the pressure. While if I'm asked under what conditions do real gas differ from ideal gas, it will be under a very high pressure and a very low temperature, because molecules in that case will be more close together, and in that condition, under these conditions, there will be a considerable attraction forces between the molecules. The general gas equation for ideal gas is a equation that relates the pressure, volume, and temperature. For the ideal gas, we write it as BV equal nRT, where B will be my pressure, V will be the volume of the gas, and N is the number of moles of the gas, while R is the gas constant, which has a value of 8.31 joule per Kelvin per mole. Temperature will be my last parameter, and it will be equal to Kelvin. So let's take an example. Calculate the volume occupied by 0.5 mole of carbon dioxide at pressure of 150 kilopascal and temperature is equal to 19 degrees centigrade. So I need first to convert my pressure into pascals. So I need to multiply 150 by 1000, which is equal 150,000 pascal. And I need to convert my Celsius temperature into Kelvin. So 19 plus 273, and this would be equal to 292 Kelvin. Now the gas law states that BV equal nRT. This means my volume is equal to nRT over B. If I looked at this, the value, if I substitute the value, N is equal 0.5, while the R is a constant, which is equal to 8.31, and the temperature, the one I calculated in Kelvin, and the pressure in Pascal, 150,000. And this would be equal to 8.09 multiplied by 10 to the power minus 3 cubic meter. If I needed to convert this one into cubic decimeter, this means I can multiply in 1000. So it is equal 8.9 cubic decimeter. Let's look at another example. Calculate the volume occupied by 272 grams of methane at a pressure of 250 kilopascal and temperature of 54. First, I have the grams and I have the molar mass of methane. So I can calculate the number of moles, which is equal to N. N would be equal M over molar mass of methane. So the 273 divided by 16 would be equal to 17 moles. And I need to convert my temperature, so temperature into Kelvin would be equal to 327, while the pressure I need to convert the kilopascal into pascal, which is equal to 250 multiplied by 1000, so 250,000 pascal. Now if I looked at my volume is equal nRT over B, which is equal to my N is 17 and the R is constant equal to 8.31 and temperature is equal to 327 and for P is equal to 250 Pascal, 50,000 Pascal, which is equal to 0.185 cubic meter. If I convert it into decimeter, it would be equal to 185 cubic decimeter. So like we see here, we can calculate relative molecular mass experimentally and from knowing the gas syringe volume before and after injection, we can know the volume of the vapor produced if I use the liquid that vaporize quickly, and the mass of the hypodermic syringe will be the difference of the mass of the hypodermic syringe will be my mass. Let's take an example. When 0.08 grams of liquid X was vaporized at 100 degrees centigrade and 23 cubic centimeter of vapor was formed, the atmospheric pressure was 1.02 multiplied by 10 to the power 5 Pascal. Calculate the relative molecular mass of my liquid. So first, if I have the mass, so first I can use the relation N would be equal to BV over RT. If I substituted in that case, my B is in Pascal 1.02 multiplied by 10 to the power 5 multiplied by the volume. You could see that the volume in that case in cubic centimeter. To be able to convert cubic centimeter into cubic meter, I need to multiply by 10 to the power minus 5. Now if I divided by R, I have R equal 8.31 and my T would be equal to 100 plus 273. If I calculated this part, it would be equal to 7.569 multiplied by 10 to the power minus 3 because I'm finding here the N, so my unit is moles. Now if I know that N is equal to M over molar mass, this means I can find out the molar mass if I divided my mass over my number of moles. So M over N would be my molar mass, and that would be equal to, I had 0.08 grams over the number of moles, which is equal to 7.569 multiplied by 10 to the power minus 3. This would be equal to 10.57. So my molar mass is actually equal 10.57. By that we came to the end of part 1 chapter 5 video. Till next video, thank you and goodbye.